Okay, so good morning. So we had stopped yesterday at this point.
Yes, sir.
Yeah. So we had stopped yesterday at the expression for the RMS content of the waveform. So this was the waveform for which we want to find the RMS value. It is this thing. The waveform which starts at omega t equal to 0 and ends at omega t equal to pi, and then it repeats beyond this. And here we are told that because it is RMS, it is root, its mean and its square. So this is the square, this is the mean, and this is the root. So root, mean and square. And we are told that we should be able to derive the expression here. Okay, so rewrite it here. Mean integration square. So VL square omega t d omega t. Since VL of omega t is equal to Vm sin omega t, therefore VL square omega t will be Vm square into sin square omega t, and since sin square theta is equal to 1 minus cos 2 theta upon 2, therefore sin square omega t can be written as 1 minus cos 2 omega t upon 2. Okay, so therefore VLRMS will be equal to 1 upon 2 pi 0 to 2 pi Vm square sin square omega t d omega t whole under root. Now we know that our load voltage is existing only from alpha to pi, and it is not existing from 0 to alpha and pi to 2 pi. That is why the limits 0 to 2 pi converted to simply alpha to pi. So we can say, since load voltage exists only from omega t equal to alpha to omega t equal to pi, so we have VL RMS is equal to 1 upon 2 pi integration alpha to pi Vm square into 1 minus cos 2 omega t upon 2 d omega t, which is equal to Vm square upon 2 pi, and we have integration alpha to pi 1/2 minus cos 2 omega t upon 2 omega t which is equal to Vm square upon 2 pi 1/2 integration d omega t alpha to pi minus 1/2 integration cos 2 omega t pi so integration of cos is sine, so we get equal to Vm square upon 2 pi 1/2 into pi minus alpha minus 1/2 and we have sine of 2 omega t upon 2 alpha to pi is equal to we can take 1/2 outside, so it becomes 4 pi sine 2 pi by 2 plus sine 2 alpha by 2. So this term will be 0. So which is equal to Vm square by 4 pi pi minus alpha plus 1/2 sine 2 alpha which is equal to Vm upon 2 into 1/pi into pi minus alpha plus 1/2 sine 2 alpha under root. Okay, this is our final expression. Okay, just one care you have to take, that the alpha here which we have to substitute will be in radians and alpha here will be in degrees. Okay, So let us just solve one small numerical here for alpha equal to 30 degrees. Okay, so we can say here compute the value of VL-AVG and VL-RMS of a single phase half wave controlled rectifier for alpha equal to 60 degrees. Solution. Okay, so the numerical is incomplete. Assume 230 volt 50 hertz supply. Solution. Given Vs RMS equal to 30 volts, 230 volt, alpha equal to 60 degrees, which is also equal to 2 pi by 3 radians, if I am right. No, not 2 pi by 3. So, pi by 3 radians, right? Yeah. And what is asked is VL which is unknown and VL RMS is also unknown. So we know that VL AVG is equal to Vm upon 2 pi into 1 plus cos alpha, which is equal to Vs RMS into root 2 upon 2 pi into 1 plus cos 60 degrees, which is equal to 230 into root 2 upon 2 pi into 1 plus cos of 60 degrees, which comes out to be 230 root 2 divided by 2 pi into 1 plus cos 60, 77.65 volt, which is equal to 77.65 volt. Okay. VL RMS is Vm upon 2 into 1 upon pi into pi minus alpha plus 1 upon 2 sine 2 alpha whole under root, which is equal to 230 root 2 upon 2 into 1 upon pi, and we have pi minus pi by 3. I told that this alpha is in rads, this alpha is in degrees. So pi minus pi by 3 plus 1 upon 2 sine of 120 degrees, which is equal to 162.6 to, and pi minus pi by 3 will be basically 2 pi by 3. So 2 into pi by 3, 2.094, 2.094 plus half of sine 120, 0.433. It will be 2.094 plus 0.433, 2.527, 2.527 upon pi under root which is equal to 162.6 into 0.897, 145.85 volts. So we get 77.65. So why I taught you how to compute it, because once formulas are known, still students tend to make mistakes because they do not take care of this thing that the alpha which is there here is actually tens, it is in radians. The alpha here has to be taken in degrees. It's very important to know. And especially in the systems like AC voltage controller, this particular formula or this kind of computation actually is needed to find the performance of the system. Okay, so now how to extend this, how to extend these formulas here, that is this thing. Yeah, so if somebody asks a question that what will be the formulas if my system upgrades to a full wave control rectifier, then it is very easy to find out. So this formula is modified and also this formula is modified. Okay, like this. So now what are the expressions for VL AVG and VL RMS of a single phase full wave controlled rectifier? Okay, so now in case of full wave controlled rectifier, we have two pulses per cycle of the input. So the waveforms look like this. 0, pi, 2 pi, 3 pi. This will be plus Vm pi by 2, 3 pi by 2, 5 pi by 2, and then we have to define alpha, pi plus alpha, and 2 pi plus alpha. Pi, 2 pi, 3 pi. Okay. There will be no conduction from 0 to alpha, and also from pi to pi plus alpha, and also from 2 pi to 2 pi plus alpha. Understand here that we have some devices which will conduct during the negative half cycle. That is why, unlike a single phase half wave control rectifier, we will be having a non-zero load voltage in the negative half cycle, that is from pi to 2 pi. So here the waveforms will be drawn like this. Again, nothing from pi to pi plus alpha. Pi plus alpha, there is somebody who is conducting. Again, nothing from 2 pi to 2 pi plus alpha. Okay. So my drawings are not symmetric, but understand that these and these are all symmetrical. So very simple. The load voltage will be doubled in case of average content, but it will not be exactly doubled in case of the RMS content. When I write the formulas, you will come to know. So I have VL AVG double that of before. So previous it was Vm upon 2 pi. It will be now double of that. So Vm upon pi into 1 plus cos alpha. And as far as VL RMS is concerned, there is only one change, that previously it was Vm upon 2. Now it will become Vm upon root 2. So we will come to know that by how many times the average content and RMS content has multiplied when we shift from a half wave system to a full wave system. Okay. Otherwise, the inside bracket continues to remain the same. Pi minus alpha plus 1 upon 2 sine 2 alpha whole under root. Okay. So if I say this is VL dash and VL RMS dash, then we understand that previously, if this is full wave system and this is half wave system, then VLAVG previously was simply equal to Vm upon 2 pi into 1 plus cos alpha. So we can say that VLAVG dash is equal to VLAVG multiplied by 2. Okay. And previously VLRMS was Vm upon 2. So basically Vm upon root 2 happens to be 0.71. So which is equal to 0.71 times Vm into this bracket, and previously we had VL RMS was equal to Vm upon 2 into the big bracket, that is equal to 0.5 times Vm. We can say that VL dash RMS for full wave system has got multiplied by a factor of 0.71.5. It is 1.42 times is equal to VL RMS into 1.42. Okay, so these are the conclusions for the two systems when we shift from half wave to full wave system. Now if we consider a AC voltage controller, also known as AC regulator, the circuit is like this. We have a single phase AC here, Vs, and we have a load here, and in between both of them we have a back-to-back connection between two SCRs. The first SCR is fired at alpha during positive half cycle, and the second SCR is fired at pi plus alpha during negative half cycle. That means this SCR, it will conduct from alpha to pi during positive half cycle, and the current will flow like this. Am I audible?
Yes, sir.
Yes, sir.
Hope my OneNote screen is also visible again.
Yes, sir.
Okay,
Yes, sir.
fine. Okay. So the lower SCR will conduct from pi plus alpha to 2 pi during the negative half cycle. So this will conduct from pi plus alpha to 2 pi during negative half cycle, and the current will flow like this in the opposite direction. Okay, that means the load resistor will experience a bidirectional current. During positive half cycle, the current will flow from top to bottom and bottom to top during negative half cycle. So we have bidirectional current. This is a circuit which is different than a converter. In converter, the load current is unidirectional. It flows from top to bottom, but here it flows in both the directions. So current is sinusoidal, and that is why for this kind of circuit, if you want to draw a waveform, then it will be drawn like this. VL of omega t, yeah, pi, 2 pi, 3 pi, and here we have plus Vm and we have minus Vm. And here we have our points alpha, pi plus alpha, 2 pi plus alpha. Load voltage waveform will go like this. Yeah. This, nothing from pi to pi plus alpha, again go like this. Nothing from 2 pi to 2 pi plus alpha. Okay. So we have alpha, pi, pi plus alpha, 2 pi, 2 pi plus alpha, and 3 pi. So now, if we assume that both the SCRs, T1 and T2, so assuming both SCRs are exactly identical. Now understand, students, that this particular portion during positive half cycle is because of SCR T1, and this particular pulse is because of T2. So if T1 and T2 are identical, then the area from alpha to pi is exactly equal to the area from pi plus alpha to 2 pi. Okay. So if I assume that both SCRs are exactly identical, I can say area of the pulse from alpha to pi is exactly equal to the area of pulse from pi plus alpha to 2 pi. Okay. And we already told that the average value of any periodic waveform is nothing but the algebraic sum of the areas above and below x-axis. We already told this before. So we already know that the average content of any periodic waveform is the algebraic sum of the area above and below x-axis. Okay, so average content of any periodic waveform is the algebraic sum of area above and below x-axis. Okay, now the area above x-axis is equal to the area below x-axis. That is why we can say, thus the VL AVG is equal to 0 for the above waveform. But the RMS content will not be 0. RMS content will be little less than 230 volts. Why so? Because see, if suppose I add this much portion to the waveform, so now here this portion is not there at all. Similarly, this portion is also not there at all. Similarly, this portion is also not there at all. Suppose if I add that portion here, suppose if I add this much portion, suppose if I add these portions to the waveform, then it becomes a pure sine wave. So that is why we'll say here, if the cut portions shown by green, if the cut portions are added to the VL waveform, then it becomes a pure sine wave. Okay, for which the VLRMS will now be equal to the input, which is equal to VSRMS, that is equal to 230 volts. Okay, So what should be the expression for VLRMS here? So in this circuit, basically we are interested to do an AC to AC conversion, and we know that AC means RMS. That means we are not interested in the average content. Anyways, we have already discussed that the average content of this waveform is 0. So what is the expression for VLRMS of this waveform? The expression for VLRMS of this waveform is such that if I put alpha equal to 0, the value comes out to be equal to VSRMS, right? So which is that expression which will fulfill this need? So VLRMS is now written as Vm upon root 2 into 1 upon pi into a brace bracket pi minus alpha plus 1 upon 2 sine 2 alpha. Okay, somebody may, sir, this is the same expression as the expression we had written for a full wave control rectifier. Okay, so I can make a comment here. Make a comment here that the above expression is same as that for a single phase full wave control rectifier. Why so? Okay, very simple. So we can bring that directly from there to here. And this waveform is like this. So if we carefully see these waveforms, then because it is RMS, that is why it is same. So I will just complete the waveform. It has got cut somewhere, right? So when I perform RMS analysis for this waveform, that is this thing. So when I perform the RMS analysis on the pulse existing from pi plus alpha to 2 pi, it gets inverted here. So basically this becomes this. Okay, so we can write down that so we can say this is figure 1 and this is figure 2. So when we subject the waveform in figure 2 to root mean square analysis. The negative pulse existing from pi plus alpha to 2 pi becomes positive, that is, it gets mirrored about the x-axis, thus making it identical to the waveform in figure 1. Okay, that is why the expression for the VLRMS of an AC voltage controller is the same as the expression for VLRMS of a full wave control rectifier. So now if you want to check if our claim was right, then we can say put alpha equal to 0 in the expression for VLRMS of AC voltage controller. So VLRMS is equal to Vm upon root 2 into 1 upon pi into brace bracket pi minus alpha plus 1 upon 2 sine 2 alpha under root, which is equal to Vm upon 2 into 1 upon pi minus 0 plus 1 upon 2 sine 0 degrees by 2. So it becomes equal to Vm upon root 2 into 1 upon pi into pi by 2, which is equal to Vm by root 2, which is nothing but equal to Vs RMS. Okay, so VLRMS is equal to Vs RMS for alpha equal to 0. So VLRMS is equal to Vs RMS if for alpha equal to 0 degrees. Okay, and if alpha equal to pi, that means if we go on extending alpha in this direction, if I go on extending alpha, so if alpha goes on increasing, then this particular thing will go towards pi and this will go towards 2 pi. Okay, so for alpha equal to pi, we have VLRMS is equal to Vm by root 2 1 upon pi into pi minus alpha, which is pi, plus 1 upon 2 sine 2 pi, which is now equal to Vm by root 2 0 plus 0 . Okay. So while this is not a part of the syllabus exactly, but this will go a long way to help you by yourself derive the expressions for both VL AVG and VL RMS for all different circuits if only the load voltage waveform is given to you. That is why this discussion was important. So in the subsequent lectures, we are going to just justify that what are the VLAVG, VLRMS values for different combinations. Okay. Yeah. Anybody has any questions or doubts they can ask. We have 2 more minutes.